I'm Dave Nicholson from the Futurum Group. Welcome to this installment of Insights from the AI Lab. I'm joined by Brian Martin from Signal 65 and Seamus Jones from Dell Technologies. Gentlemen, good to see you again. Welcome.
Dave,
Hi guys.
Seamus, great to see you again.
So today we're going to dive into this topic that's interesting because topic and topology are kind of related in a way. But the question is, why is networking even more important than it's ever been in the past? And we want to dive into some of the questions about how network topologies affect the kind of performance you can get, the kind of scalability you can get for both inferencing and training environments. You've collaborated to come up with kind of a case study, white paper, a lot of real world testing in Signal 65 labs. Seamus, what was the point originally going into this? What were you hoping to discover?
Yeah, I think it's no surprise, right? As we have historically had topologies that were set up for a compute-bound framework, right? Ensuring that they have performance for those compute architectures. And really with AI, what we're seeing is that it's more of a communication-bound AI workload, and that framework as having a much broader impact on the performance of these AI clusters when you have these highly performant GPU frameworks in place. And if you don't have the right topologies, it really can cause bottlenecks that were unforeseen. So you'd be spending all this money, effort, time, energy in developing topologies or developing systems in the data center, but then you're then throttling them artificially by your topology. And so we wanted to make sure we were able to, Brian and I discussed it. And we're like, this is a topic that continually comes up with customers. How can we give some good sound advice that's based in fact?
And so what did the kind of configuration look like? What did the stack look like that you tested, Brian?
Well, so we looked at three stacks predominantly. We looked at traditional leaf and spine clone networks configured in what's called a fat tree. So full bisectional bandwidth between all endpoints. This used to be sort of the premier high-end best network you can build. And then we looked at what's evolved called rail optimized, where researchers noticed that most GPU traffic stays within a particular GPU stack or rail. So say GPU 0 on all the servers tends to talk to other GPU 0s far more often than it does GPUs 1 through 7 in other servers. So they were able to take the concept of a clo-fat tree, do a rail optimization on it, and instead of all GPUs talking to any other GPU equally, they said, let's focus on GPUs in a specific rail talking to each other, 8 GPUs per server. Suddenly we have 8 times as many servers in a 2-tier network topology. So we can go from 1,000 servers and 8,000 GPUs to 8,000 servers and 64,000 GPUs in a single 2-tier fabric. It's nuts.
Yeah.
Anything surprise you, Seamus, about the results, or were they kind of in line with what the math showed before you actually ran tests?
Yeah, I mean, when you looked at the math, the costings didn't completely line up on the optics. I think one hidden cost that I didn't expect, especially in the framework, was the fact that you can drive a lot of power requirements or a lot of power consumption and a lot of cost through the optics that you choose. I know it sounds crazy, but the second you get up into the 6,000, 60,000, optic numbers, you're looking at a large amount of cost and a large power draw. So by going to things like LPOs versus copper, you're actually reducing costs straight away. The other thing that we looked at that I thought was really interesting was the sweet spot for most customers today is really looking at how they can have the lowest cost and the highest scale, right? Mm-hmm. And in a reasonable fashion. I think the rail optimized really pointed that out. Rail, not rail optimized. So the rail framework having a dense LLM for training and even having a framework for a model of experts inferencing, that rail architecture really made a big difference.
So when you MOE, modeled experts, mixture of experts. We love our TLAs, 3-letter acronyms, and but it's saying exactly what you're saying. Brian Martin, just give us 20 seconds on what does that mean to have a model that is leveraging a bunch of experts or a mixture of experts?
Got it. So the big thing with mixture of experts, a traditional model LLM, say it has 72 billion parameters. All of those parameters are active at once, which means the GPU is processing tensor vectors through those, all of them for every operation it does. A mixture of experts you can think of as a collection of smaller LLMs being called upon when it's appropriate. So imagine having a room with 16 experts, and I have a question about medicine or a question about law, and I activate the lawyer, always activate the lawyer, and the doctor, or I have a civil engineering question, activate the civil engineer expert. So experts activate, and then we see across systems one of two effects: either a much lower GPU impact because we have only 8 or 10 or 12 billion parameters active instead of all 72, or on the flip side, we can run a much larger model, hundreds of billions of parameters because I only have 72 active at the same time. So it really opens up that field.
That sparsity or task routing really means that you're able to get much more efficiency in that mixture of experts. Thank you for the correction there, Dave.
Oh, it wasn't a correction because people use it both ways.
I mean, in a Llama 4 Maverick model, that's a perfect example of a mixture of experts model. We're able to see a dramatic difference in performance if you're able to actually have those tasks routed to the right expert, like what Brian was talking about.
Well,
Makes
so
a big difference.
The lawyer model, all it needs to do is just generate the response "no" over and over and over again. So
For corporate lawyers, right?
It would seem that it's got the lowest power draw. But from a Dell Technologies perspective, Seamus, do you think that this whole mixture of experts idea is something that is likely to be kind of omnipresent in a lot of environments that you guys are working on?
Absolutely. What's happening is that, we're in the age of agentic AI, right? And having mixture of expert models. So that's a tough one to say over and over again. It really means that we're able to dedicate that traffic through dedicated hardware like 4 NICs or Tomahawk switches through the Dell networking portfolio. And it means that we can use these lossless Ethernet fabrics to get the best performance possible, right? Instead of having just broadcast, right, within other topologies, we're able to use this framework to make sure we get the best performance. So it will not go away. It's actually going to get even more robust over time. Yep. And as the fabrics become even more performant, we're going to see it become critically important as well.
Yeah, and it's kind of Brian, there's sort of interesting parallel here because it's not like this concept of fit for function, right tool for the right job is new, right?
Right.
But it's finally, we're embracing it in the world of AI. From a Dell Technologies perspective, you can sort of see that it's analogous to the decisions about hardware that are being made. And this is a question for you, Brian Martin, because you're the a little more objective than Seamus,
unbiased,
since he's part of Dell Technologies. But the idea of Dell being kind of the Switzerland of infrastructure for these environments, how important is that? How important in this testing was it to know that that the Dell networking that was involved adheres to open standards as an example?
I was just going to say that, Dave. That's a great lead in. Being open, standards-based, scalable means a couple of things. One, it really shows up on the TCO cost line, but not just in the hardware purchase, but also in operations and management. Managing well-known switch technologies, Ethernet technologies is something that our workforce has some experience with, and that really contributes to overall lower management and operational costs, in addition to capital acquisition costs. These are the things we've known and loved, or at least known and worked with for years at scale.
What did you find interesting around working with Sonic specifically? Because Sonic as a framework within those operational costs. I mean, we have unified instruction sets. We work on Sonic-based standards. But I wanted to see what your take there was.
Standards based, especially when we're testing multiple topologies and configurations in a dynamic lab. The simplicity around management, programmability, whether it's API based, CLI based, configuration based, to configure, set up, reconfigure, reload, save. Sonic is a great environment to work in.
You know, I asked Seamus the question about, was there anything surprising that came out of this? I'll throw this question out to both of you. What are some misconceptions that people might have who are starting to take a look at networking in the area of AI? One thing we haven't mentioned yet is this idea of training something like a frontier model and how that might be different than specifically than the inferencing side. But what would you expect people to not understand very well?
One thing that literally came up last week was their perception was that they could invest in some of these high performance NVLink based architectures, like the XE9680 with H200 GPUs, and they wouldn't necessarily even consider re-architecting their networking architecture to optimize that system, because they didn't even consider the GPU fabric on the back end. And they thought, well, we could just implement it into our existing fabrics today. And there's definitely a shock factor that comes in place when you start talking about, no, it's critically important. I mean, you think about each of those GPUs as 10 GPUs, 10 connections out of the back of that box. And you can have multiple high performant, low latency fabrics off the back of that. That builds up a number of ports immediately. And if you start to scale those numbers out, it really becomes really interesting. Frontier models, what you're talking about, I mean, that's like, what do they call it in the Tesla? The insanity mode, or, the insanity function, where it goes full performance, full connectivity all the time on rail optimized architectures. So it's even the next step beyond rail. And it means that we can scale to exceptionally high levels, just beyond. Brian, what were the numbers on that one?
Rail optimized for a 2-tier network is 8,000 servers and 64,000 GPUs.
Exactly. Yeah, 64,000 GPUs. I mean, I wish we were selling more opportunities with 64,000 GPUs, right?
I want to be in the power business. I'm trying to figure out how to invest in the where does the electricity come from business. Brian Martin, I don't know if you wanted to follow up on what Seamus was saying.
I did. You asked sort of what really came surprising. What struck me through this project is I was working on like drawing, architecting. First, just keeping track of everything is almost mind-numbing. But at one point, it dawned on me that after spending over a decade in storage and fine-tuning storage area networks and the criticality of storage networks, in the GPU world, those networks are orders of magnitude bigger and faster, higher bandwidth, more important. What used to be the premier network is now just called the front-end network. It's like the storage isn't also ran in these environments.
Yeah,
it was a little mind-boggling.
Well, I've got kind of a little flyer of a question to wrap on. I think I calculated that between the three of us, we have something like 275 years of experience working with IT infrastructure, something like that, plus or minus 2 or 3.
Accurate.
And so I think we would all agree that data is at the center of what we do with all of these tools, AI or not. First, I want to start with your thoughts on this, Seamus. People are really concerned about the difference between having data available to be retrieved versus training a model on their data, and specifically where their data lives. Dell has been delivering infrastructure to the largest cloud providers on earth and the smallest companies on earth. So you don't necessarily have a specific dog in the fight when it comes to that. But are you seeing more people want to run these things within their own walled gardens or on premises in a way that may have shocked proponents of cloud from 5 years ago? Long question, but I think you get the point. What are you seeing out there?
Yeah, I mean, to your point, 5 years ago, there were a lot of companies that had a cloud first and cloud only objective. We're definitely seeing a change in that perspective. While cloud is still, a lot of workloads are still being deployed in cloud architectures. And I don't think that'll change. Things like Salesforce, SFDC, like some things like that. But the problem that we're seeing is that a lot of customers' proprietary data has gravity. But we always talk about that fact. And just to point it out, we've done a lot of customer POCs, or what we would call, sometimes we call them POVs, proof of value, right? And so what we do is we implement, what the customer's trying to achieve in their data center on-prem. And what they're finding is that, look, if I was to do these POCs using cloud architectures, because it's very easy, quick, and capable to deploy these in the cloud. I could spin up a GPU in the cloud on a hosted service very inexpensively and very quickly. However, the data, but when you're not using your own data set and you're using cloud-specific tool sets to build your AI applications and workloads, then it doesn't necessarily translate to the same proof of value as it would when you're on-prem and you're dealing with your own data and you're doing that at scale, right? So really a critical piece that we're seeing is that a lot of these customers not only are deploying production level AI deployments on-prem, but they're actually looking to do POCs, or what we would call proof of value, POVs, on-prem as well, just to show, look, does this show value to our business or not? Because quite often, if you do one in the cloud and then you translate that to an on-prem architecture, it doesn't translate, right? So it's really critically important, and that's why we developed this lab, this architecture, this infrastructure, so that customers can do an on-prem POV remotely in our lab that Signal 6.5 has helped us deploy. So we have physical architecture that we can transport data and have a framework that would replicate and simulate a customer's environment exactly, right? That's the objective. So we're showing better POV. It's a long answer. The bottom line is yes. I'm going to give you the quick one. Yeah, people are moving to an on-prem, framework, especially for these data sets that have gravity. They might be security concerns. They might have consistent changes. All these things. But yes, on-prem has definitely, like hardware has become cool again. On-prem is definitely seeing a resurgence.
Brian Martin, why do you hate hardware so much?
It's just been my life. It's great that it's cool again. Organizational data has been and continues to be the crown jewel. And in this world of AI, access to meaningful value from that data is growing exponentially. So having the compute close to the data and within the security zone definitely makes sense.
And just a little sanity check here. None of us has signed over power of attorney to an AI agent yet, correct?
Not yet. Hold on. let me turn off my AI agent to respond to that.
Yeah,
exactly.
Exactly. Any final thoughts on this? Anything we missed? We're gonna have links to the white paper.
Yeah, one parting thought, Dave. For what I'll call modest environments, As Seamus mentioned earlier, the optics and the connectivity on these switches contributes a lot more than we expected to cost and power. If you only need 1,000 servers and 8,000 GPUs, then a single tiered rail architecture can do that with 8 switches instead of the 96 switches that would be required in a traditional leaf and spine. That's a dramatic savings.
And it adds up. It adds up. I was actually using an AI assistant to help me run some scenarios on power. We're hearing a lot about 10 gigawatt data centers. If you were to try to power that 10 gigawatt data center with only photovoltaic solar, you would require 400,000 acres of solar panels. The state of Rhode Island is 420,000 acres. Then on top of that, because the sun doesn't shine all day long, you would need the equivalent of 1 million Tesla Cybertrucks worth of batteries. And the estimate to build that out, it's between 80 and 100 billion dollars to power one of those 10 gigawatt data centers. So at scale, when you start talking about the efficiencies that you're referencing, it's extremely meaningful. And yeah, offline, let's figure out how we can all get rich investing in power. But with that, I want to thank both of you for being here. Another great conversation. We'll have a link to the white paper supporting documentation for those who want to dig in more deeply. For the Futurum Group and Signal 65 Labs and Dell Technologies, I'm Dave Nicholson. Thanks for tuning in to this episode of Insights from the AI Lab.